Welcome back. In this video, we will introduce the uniform distribution, revisit the exponential, and talk a little bit about expected value and variance for continuous distributions. So we'll start with the exponential, or the uniform distribution, We'll then move on to expected value and variance of a continuous random variable, followed by a talk about the exponential distribution. So we say that a random variable y is uniformly distributed over some interval a to b if the density function looks like this. If we can write the PDF as 1 over b minus a for a less than y less than b. Essentially, if our density function is a flat rectangle, we have a uniform distribution. So let's take a look at an example working with the uniform distribution. The convenient thing about the uniform distribution is because of its flat geometric shape, we actually can skip integrating to find probabilities. We can just find the area of a rectangle. So Beth is traveling from Omaha to Denver, which is a distance of 547 miles. She plans to stop at Kearney, which is 185 miles from Omaha, but she falls asleep immediately in the car. When she wakes up, what's the probability that Beth is past Kearney? So we'll assume that the amount of time she sleeps is uniformly distributed. We will also assume that she is not the driver. Furthermore, Beth is then equally likely to wake up at any point in the journey. So y is the distance that Beth has traveled. The probability that she wakes up before Kearney is the probability that y is less than 185, so 185 over 547, or 0.338. The probability that she wakes up after that point by the complement rule is then 1 minus 0.338, or 0.662. The advantage of the uniform distribution is that it is very quick to find associated probabilities. The disadvantage is that it's probably not realistic for a lot of situations in practice. Now for a uniform distribution, the CDF is found like this. Up to point A, where the distribution really begins to have some probability support, the CDF is 0. There's nothing that's occurred to that point. The probability that y is between A and B, or the probability that y takes on a value up to or between A and B up to that point cumulatively is y minus a divided by b minus a. Probability that y is greater than b, or cumulative probability I should say, is then 1. Now let's talk about finding expected value and variance for continuous random variables. Essentially, these are defined in the same way. The expected value is still found by taking y times the PDF, however now we're integrating instead of summing. The variance becomes the integral of the quantity y minus the expected value of y quantity squared times the PDF dy. To find expected value and variance for continuous random variables, just integrate instead of summing. The nice thing is that all of the properties that we've learned already continue to hold. So let's apply these definitions and try to find the expected value and variance for the uniform distribution. The expected value of the uniform distribution is the integral from a to b of y times the PDF, which is 1 over b minus a dy. So we get 1 over b minus a times 1 half y squared, evaluated from a to b, which is 1 over 2 b minus a times b squared over a squared. With a little bit of algebra, that simplifies to a plus b over 2. So in other words, the expected value of a uniform distribution is simply the midpoint of the range. To find the variance, we'll use that computational form of the variance because it's a little bit quicker to work with. We'll take the expected value of y squared, so that's the integral of y squared times the PDF dy. So we get 1 over b minus a times 1/3 y cubed, evaluated from a to b. Expected value of y squared is 1 over 3 times b minus a times b cubed minus a cubed, which turns out to be, again, a little bit of work here. We get a squared plus ab plus b squared over 3. Now, in order to find the variance here, the variance is the expected value of y squared minus the expected value of y quantity squared. So we will combine like terms, do a little bit of algebra, and at the very end, here is what we get. The variance of y is b minus a quantity squared over 12. So this is the expected value and variance of a uniform distribution. Now here are some properties of the expected value and variance for continuous random variables. We can pull constants out like we did before, so the expected value of ax plus b is a times the expected value of x plus b. The expected value of x plus y is the expected value of x plus the expected value of y. The variance is the expected value of x squared minus the quantity expected value of x squared. In order to pull a constant out of the variance, we need to square it. So the variance of ax plus b is a squared times the variance. And then finally, to get the expected value of any function, we can simply integrate that function times PDF. Now let's take a look at the exponential distribution. So we say that y has an exponential distribution with parameter lambda greater than 0 if we can write the PDF in the following way. If little f of y is equal to lambda times e raised to the negative lambda y power. We say that this is true for y greater than 0 and 0 everywhere else. Some properties of this exponential distribution. The PDF of the exponential is a result that we've shown previously to be 1 minus e raised to the negative lambda y. The expected value of y is then 1 over lambda. The variance of the exponential is 1 over lambda squared. So let's say that we have an IT help desk that is receiving phone calls throughout the day. The time between these calls is modeled with an exponential distribution with mean 4 minutes. We have a call that has just come in. What's the probability that we will get no call in the next 5 minutes? So we will let y be an exponential distribution. We know that the mean time between calls is 4, so the parameter lambda is then 1 over 4. The probability that y is less than or equal to 5 is the integral from 0 to 5 of 1/4 e to the negative y over 4. We can actually go straight to the CDF since we know what this is. So the CDF evaluated at 5 is 1 minus e raised to the negative 5 over 4. The probability that there will be a call in the next 5 minutes is 0.71. So then, in order to find the probability that there will not be a call in the next 5 minutes, we'll use the complement rule. So 1 minus 0.71, about a 29% chance. Looking at this distribution, in order to calculate these probabilities and work with the exponential distribution in R, we will need to parameterize things just a little bit. The rate parameter here is the lambda. So since our expected value is 4, our rate is 1 over 4. Now the exponential distribution has a special property to it. It's what's called memoryless. So we'll let x be distributed exponential lambda. Let's find the conditional probability that x is greater than s plus t, given we know that x is greater than s. So starting with the definition of conditional probability. In the denominator we have our condition, the probability that x is greater than s. Normally in the numerator of this conditional probability we have an and symbol. However here it's strictly not necessary. In order for x to be greater than s plus t, x must also inherently be greater than s. So that's why our numerator is just simply the probability that x is greater than s plus t. We'll use the CDF here to help us find those probabilities. So it's 1 minus the CDF evaluated at s plus t divided by 1 minus the CDF evaluated at s. We then get e raised to the negative lambda times the quantity s plus t in the numerator. Denominator e raised to the negative lambda s power, so we get e to the negative lambda t. Here's what this really tells you. The probability that an event does not occur in some time interval of t units, so say s to s plus t. As long as we're conditioning on getting to that previous point s, that's the same as the probability that it does not occur in the interval from 0 to t. So an interval of t unit length probability, or t unit length, has the same probability as long as we're conditioning on reaching the starting point of that. So that's what we mean when we say memoryless. Let's take a look at an example using this exponential distribution. So 1 hour carbon monoxide concentrations in air samples from a large city have an approximately exponential distribution with mean 3.6 parts per million. Let's find the probability that the carbon monoxide concentration exceeds 9 parts per million during a randomly selected 1 hour period. Will this probability change if we can reduce the mean carbon monoxide concentration? So I'll let Y1 be the carbon monoxide concentration in air samples. Y2 will be the same concentration under the new traffic control strategy. We know that the mean for Y1 is 3.6. The mean for Y2 is 2.5, both in parts per million. So the probability that Y is greater than 9 is 1 minus the CDF of Y1 evaluated at 9, so about 0.08. However, if we do the same calculation for Y2, the probability of exceeding 9 parts per million under this new distribution has decreased rather dramatically. It's gone from about 0.08 to about 0.03. So here is what those two distributions look like side by side. Without traffic control, there is a higher mean, higher probability of reaching a value greater than 9. With traffic control, the exponential mean has shifted downward. It's become lower. There's a smaller probability of reaching 9 units. We will stop here with this video. In the next video, we will continue to introduce some more continuous distributions. See you then.